Okay, let's move into the last chapter finally that we're going to cover this year. And I don't know that we'll get to cover all of it, but I want to cover a lot. Now, notice I'm not using the book's PowerPoint for this because I don't like the order they do this at all. They do it exactly backwards from the way I like to do it. So I'm using my own homemade PowerPoint. I know it's not chapter 5. That references a different textbook, my favorite Chang book. So in your book, this is chapter 11. But again, what they cover in the beginning of the chapter, I'm going to push till the end of the chapter and cover it there. And so things are going to be jumbled up a little bit. So in this chapter, we're going to look at the behavior of gases. Why gases? Because they're cool. They can expand and contract. You heat them, you compress them, whatever. Normal things like solids, liquids don't do that. And so the expansion and compression and all that of gases led early scientists to start examining this closely and discover mathematical principles behind it. So discovering the mathematical principles behind the expansion of gases and things like that ultimately gave them the idea of putting math into the sciences and led into chemistry becoming a real science. So this is of historical interest, of course, and of course these gas laws, as we know them, play an important role in the development of thermodynamics and steam engines in the Industrial Revolution. So it's significant stuff. So first of all, I want to talk about what makes something a gas. In a gas, the particles, molecules, are moving around at very high speed. In a solid, the atoms are packed tightly together and they're just jiggling around. In a liquid, they're kind of packed together and they're slipping past each other. But in a gas, the molecules are freely flying around in all directions, and they're spread very far apart. Now, the temperature of the gas determines how fast the molecules are moving on average. Every molecule is moving at a different speed, and when it bumps into another one, it may speed up or slow down. So it's a chaotic mess. We talk about the average speed, and that's the temperature. The higher the temperature, the faster they're going. The more likely they are to fly apart from each other. Now, on the other hand, these molecules are all attracting each other. They have intermolecular forces, as we call them. Why? Because the nucleus, the protons in the nucleus of one atom or one molecule are attracting the electron cloud of a nearby neighboring molecule, and vice versa. And so molecules are kind of sticky. They tend to attract each other. Now, if they're moving very slowly, when they get near each other, those attraction forces can make them stick together. And if that happens, then they'll liquefy out and become a liquid or even a solid. But if you heat it up, the molecules move faster and faster. And at some point, they're moving so fast that by the time the attraction forces had the chance to pull them together, they're already past each other. And so you make it hot enough, and they're moving so fast they can't attract well enough, and they fly apart and become a gas. So notice the temperature matters. The hotter you make it, the more likely it is to become a gas. The strength of the intermolecular forces matter. If I have a molecule like hydrogen, the H2 molecule that has very, very weak forces, you can bring the temperature down really low, close to absolute zero, and those weak forces aren't enough to pull it together, and so it stays a gas. You got to get down really, really cold to make hydrogen liquefy or solidify into hydrogen ice, down near absolute zero. On the other hand, you take a molecule like the water molecule that has very strong intermolecular forces. Even at room temperature, which isn't ridiculously hot, but even at that temperature, it's hot enough that it's cool enough that those attraction forces can make it stick together. And so the water molecules don't go away as a gas, they stick together as a liquid. Hydrogen molecules had to be down near absolute zero. Water molecules are doing it at room temperature. Why? Because they got stronger intermolecular forces. So hotter temperature makes it become a gas, lower temperature makes it liquefy or solidify. Where's the cutoff? Depends on how strong the intermolecular forces are. Each gas, each substance will have its own cutoff points, and that's the melting and boiling melting and boiling points. So I wanted to have that discussion. Now, Don't worry too much about this. Some gases are just made of individual elements. Some are compounds, like HCl, carbon dioxide, whatever. Ionic compounds have very, very strong forces. They don't become gases, at least not at normal temperatures. You got to get ridiculously high, like surface of the sun hot. So that's not important. The discussion of intermolecular forces and temperature is. Now, in discussing gases, at least early on, there were three major factors that they had to deal with: volume, temperature, and pressure. Volume is the amount of space that the gas takes up. How big is your balloon? Put more gas in, it expands and you get a bigger volume, right? So we know what that is. It's measured in cubic meters or liters or milliliters as unofficial units. Temperature, we just talked about that briefly. It's the molecular motion. The faster the molecules are going, the higher the temperature. That's measured in kelvins or unofficially degrees Celsius. And of course, we don't use the F word here. Pressure is something we haven't talked about yet. Pressure is the amount of force per unit area. So if you push down with the surface of your hand on your whatever desk is in front of you right now, whatever force you're pushing with is spread out over the surface area of your hand. And what you feel is pressure. If you push with greater force, you're going to feel greater pressure in your hand. But also, take the same force, but push just on the tip of your finger instead of the whole palm of your hand. You're going to feel greater pressure. Why? Because that force is concentrated on a smaller area. So pressure is how much force you're applying, but also how concentrated on it is. If that force is concentrated on a tiny area, you got a lot of pressure. So if you're walking around on high heels, the force of your weight is all concentrated in those heels and you sink into soft dirt and mud or whatever. Whereas if you walk around on normal shoes, you might not sink in as readily because your weight force is spread out over a bigger area. Mathematically, that's pressure equals force over area, which we're not going to really do anything with that. In physics you might, but not here. The unit of pressure, force is in newtons, area is in square meters. So pressure is in newtons per square meter, which we're going to just give a name and call it a Pascal. That guy up there is Blaise Pascal, the guy we named it after. So the SI unit of pressure is the Pascal or PA. Now, normal pressures are so high that we need thousands, tens of thousands, hundreds of thousands of them. So usually we tend to work in kilopascals instead. Now, normal air pressure, the air pushing down on you, it's a gas, it has weight, it's applying force on you. Air produces pressure. Standard air pressure, which is defined as the pressure on an average day at sea level on Earth, is 101,000 pascals. So again, notice we use kilopascals. 101.325 kilopascals is standard air pressure. Again, that's a typical day at sea level. We live a little above sea level, so normal day here is probably going to average less than this by a little bit. But we define this to be standard pressure. So if I ever tell you convert to standard pressure, this is the pressure you should look for. 101.325 kilopascals. Now, yes, we have the regular unit, but now we make up unofficial units. We always do that. So that standard pressure often we'll call 1 atmosphere of pressure. 1 atmosphere is just 101.325 kilopascals. It's the standard pressure on Earth. Why would we use that? It's a nice, easier number to work with. Also, it gives us easier comparisons. If I tell you the surface of the planet Venus has an air pressure of 90 atmospheres, it immediately tells you something about that planet. Whereas if I gave you a number in kilopascals, it's just some random big number. So it's easier to compare when you use atmospheres. Now, one other thing is, and I won't get into the details of this because we really don't have time to. If we were in school, I would show you this. You can put mercury in a U-shaped tube, a U-tube, right? And if you have vacuum on one side, so you seal off the tube and suck the air out, the other side, air is pushing down. It's going to push the mercury to unequal levels. And so they can measure the pressure of air by how far it pushes mercury up the tube. And so another unit of pressure that we use, well, don't worry about that. These devices that I'm talking about are called manometers and barometers. So another unit of pressure we have is the millimeter of mercury. Literally, how many millimeters did air push the mercury up the tube? Or any gas, not just air. Sometimes millimeters of mercury are called torrs, named after Torricelli, the guy who did some work with this. Standard pressure in this unit is 760 millimeters of mercury. So notice we have 3 pressure units: kilopascals, atmospheres, and millimeters of mercury. And notice 1 atmosphere is 101.325 kilopascals, is 760 millimeters of mercury. This is starting to sound like unit conversions to me, isn't it? And how do we deal with those? We do dimensional analysis. It's been a little while, and we did it a lot with moles and grams and things like that. Now we're going to do it with pressure units. So for example, if I give you 75.0 kilopascals, could you convert that to millimeters of mercury? Well, we know the conversion factors, right? So take our 75 kilopascals over 1, multiply by conversion factors. Kilopascals on the bottom, so it cancels. The unit we want, millimeters of mercury, on top. What's the conversion? Well, standard pressure is 101.325 kilopascals. Standard pressure is 760 millimeters of mercury. By the way, that 0 is significant. So again, you just plug in the units where they need to be, plug in the numbers to go with the units, and now just do your dimensional analysis. Multiply the top, divide by the bottom, and we get our answer. Again, we talked about conversions before. 1 foot equals 12 inches. 1 mole equals the molar mass in grams, whatever it is. Well, 1 atmosphere equals 760 millimeters of mercury. 1 atmosphere equals 101.325 kilopascals. They all equal each other, and so we can use those as conversion factors. Sound good? Now, I give you this as an example of doing your own, but let's kind of do it together. I give you 1.25 atmospheres and ask you to go to kilopascals. So I'm going to go to, I got to erase my CP chemistry here. Oops, don't want to save that. I lied. Cancel. I'm wasting time here right now. New, don't save. I already forgot what the pressure was. 1.25 atmospheres, we're going to go to kilopascals. So 1.25 atmospheres equals how many kilopascals? So 1.25 atmospheres over 1 times, all right, so we're going to put atmospheres on the bottom. That's what we're trying to get rid of. We're going to put kilopascals on top. That's what we're trying to find. Now, what numbers go in there? Well, 1 atmosphere is 101.325 kilopascals. If I had asked you to go to millimeters of mercury, I'd put 760 up here instead. Notice the unit atmospheres cancel, and now I just multiply the top. Well, divide by the bottom is just 1. I don't have a calculator nearby, I just noticed, so you'll simply have to multiply those two numbers together, and you'll get 120 something. Maybe 130-ish, depending on how far you have to go. But that's it. You simply do dimensional analysis to convert one pressure unit to another. So I'm going to stop there, and that'll be it for today. Your not homework, but your work to do for today to practice this is I'm going to give you a few pressures to convert back and forth, and we'll do some dimensional analysis with it. Once you've done that, then we can start looking at the gas laws and how to use those. And that is it for today.